Hello and good morning, everyone, to our webinar Behind the Light. Today, I'm going to present to you, together with my colleague Volker Kukula, some of the challenging details which are connected with the design of light sources for various applications. We are taking a deep dive into a lot of different technical aspects of the design, specifically the April registration and eco-design labeling, which is mandatory for a lot of light sources in the EU, operational safety requirements, dimming technologies, and thermal optimization of light sources. But firstly, let me introduce ourselves. My name is Paul Spanbock. I'm sales director and co-founder of Lumitronics, working with Lumitronics for more than 20 years now. With me is Volker Kukula, our head of engineering. We will share the presentation with you after the webinar. You will have the opportunity to download also a full video of this webinar, and you will have the opportunity, after we showed all of our presentation to you, to go into a discussion and also place all your questions. Please use the area Q&A or F&A, depending if you have German or English language activated, where you can place your questions during all the webinar already, and we will answer all of them after we finished with the presentation. Okay, I think this is all for general organizational aspects. We have a lot of participants today, almost 100, and I think most of the participants arrived by now, and we can start. I will firstly start with a short general overview of Lumitronics, so you know who's talking. We are LED specialists since the very beginning of LED technology in general lighting for white light. We have started our company in 2005, just when the first LEDs for white general lighting had been available on the market. We are doing soft and hardware development for light sources, and we are producing all of these light sources in our facilities in Hechingen in the south of Germany. We're reliant to a very unique partner network. We're working with all major LED manufacturers as official partner and with the major manufacturers of optics. We're certified with ISO 9001, 45001, and 14001 with approximately 50 employees, have a turnover of 9 million euros. We are a fully dedicated, highly specialized, mid-sized company, only specialized to the development and manufacturing of light sources. We are segmenting our business mostly to two different segments, which one of them is the production and development of the light sources, for which we are mostly doing custom light sources. So whatever type of requirements you might have, you can approach us with those, and we don't have a very specific line card of standard products, but usually are used to really customize all our light sources to your requirements. We are doing the hardware and software development for those light sources. We're doing the SMD assembly, and we have a lot of highly specialized production equipment, such as reel-to-reel production capabilities, in which we're basically using one single electronically connected PCB of length of up to 100 meters. And Besides that, we are also distributor for some of the major manufacturers of LEDs, such as Nichia, Lumileds, Bulb, and also for lenses such as Ledil, Carclo, Gajon, and Ari. So if you also have your own production and development in-house, we are very well suited to support you in the production and development process and deliver the LEDs as a component to you. But this is, I think, already enough to understand who we are, what we're doing in general. Let's go into the technical details for which you have registered. So I'm starting with the IPRA registration and eco-design labeling. I will give you a short general overview and then hand over to Volker. Today, we have two relevant regulations in the EU, which is the 2019, 2020 and 2019-2015, for which is one, it's a single lighting regulation, which is defining the minimum requirements for eco-design on light sources in the EU. And the second one is the corresponding energy labeling for the eco-design labeling. They are pretty complicated regulations with a lot of exceptions, but actually there had been a lot of different regulations before. So I think from our perspective, these two regulations are actually making things a lot more easy than it had been before. So to understand the regulations in more detail, the most important aspect from our perspective is to understand the different components which are specified within the single lighting regulation. First of all, there is the luminaire itself. The luminaire itself is actually not very relevant to the single lighting regulation anymore, as long as you are able to specify it as a containing product. Containing product means that the components inside can be measured and specified as standalone products, such as the light source, the separate control gear, and the lighting control parts. What are these specific products? I'll hand over to Volker, who can explain this to you a lot better in detail.
Yes, hello, and also welcome from my side. Thank you, Paul, for the introduction. As you have alluded to, we are now going to look at the different parts of a luminaire in order to make sure we together can understand how to design the luminaire and how to specify the luminaire in order to make your lives easier. Let's first look at what is a containing product. A containing product is a regulatory definition that what you think of a luminaire. And it might contain a light source, it contains optics, it contains separate control gear. But all of this is very easy for you if you design your luminaire to not be the light source itself, but to be able to extract the light source. So you can simply label your luminaire as this is a luminaire containing product which contains a light source of a specific energy efficiency class. Why this is important, next to making it easier for you for your registration, we will look into it in a couple of seconds. The second part of the luminaire are the light sources. Generally, a light source is the electronics which are designed to emit white light. Of course, there are numerous exceptions, and the details are quite complicated, especially if it doesn't just emit white light, but to make it short, the light source is the electronic part which really emits the lights, and it does not need to have optics or anything else. The second part is the separate control gear. We separate control gear is defined as some kind of mechanism which is designed to take mains power and to reformat it in a way that your light source can emit light. For example, this can be this will be a power supply which delivers 24 volts of constant voltage or even constant current. Again, definitions in detail are quite complicated, but you can remember that a separate control gear is mainly what you think of when you think of a power supply. We lighting control parts on the other side are parts of the luminaire which are not strictly required to emit light. For example, this is remote control or some other kinds of controls which are just doing the interface between the human user and the electronics, but is not the power control circuit or the light source itself. For example, Lumitronics is developing light controlling parts with Kazambit technology. So now that we know the different parts of the luminaire, let's look at what information requirements are required to be present on the product in order to fulfill the regulatory requirements. The information requirements are specified as being on the product itself, on the packaging, on a website, technical data sheet, and also in a database. The European Union has created a system called EPREL. This system is a central database where you have to upload your light source data, and if your luminaire is not separated from the light source, also your luminaire, in order to have a central point where all the products are comparable on and also registered. Moreover, energy labeling has changed. Most of you have seen the sticker. There are many kinds of sticker for different kind of products, for example, washing machines or even cars. But especially for light sources, with a single lighting regulation, labeling has changed. Before there was a plus plus, a plus plus plus, and the regulatory body has discovered that it's quite hard for people to understand which is really good, because before almost all of the light sources were a plus plus plus. And now with the new single lighting regulation, it's quite harder to get the required mains efficacy to get a good energy label. Now, as alluded before, let's take a look back on why specifications is easier for luminaire manufacturers. As said before, if the energy efficiency label defines how the mains efficacy of your luminaire is. And if you define the whole luminaire, then all of the efficacy losses of the power supply, of the optics, of reflectors will result in a luminaire efficacy which is quite bad. Whereas if you just define the LED module itself, you get a better lighting efficacy because all of the losses of optics and power conversion will not be included. So to combine this, define your LED module as a light source in order to get a better efficiency. Moreover, what is required to get a good rating? Of course, you should use efficient LEDs with KSF technology. And if you cannot use this technology or don't want to use this technology, you can also use tunable white functionality instead of KSF LEDs, which means if you have warm white and cool white LEDs, then you use the cool white for the specifications in order to make sure that since those are more energy efficient, you get a better rating. So combined, we know now how to register your modules to comply with regulatory bodies and also to get a good energy efficiency rating. After we looked at those legal topics, let's get into the meat of the topic, the electrical and the technical details. First, I want to talk to you about operational safety. This is a deep dive. We have extracted a couple of topics where we have, in our experience, seen that unless you're aware of these topics, it's very easy to design a luminaire or a light source which might cause trouble. So we are starting with the operational safety and especially the electrical safety, photobiological safety, and then also thermal safety and safety in case of an electrical failure. Starting off with electrical safety. It's easier for you if you design your luminaire to remain within self voltages. This is because we IEC 61140 defines hazardous voltages as everything above 50 volts DC, AC and 120 volts DC. And if you're not within those self voltages, then there are increased demands with regards to isolation, and with those increased isolations, you also need more space. And this makes it much harder to design a luminaire. So by simply being inside with self voltages, you make your life much easier to get a compliant LED luminaire. The next topic I wanted to talk to you about is photobiological safety. Again, there is a norm like for everything. We norm 62471 defines a couple of different risk groups, and depending on the risk group, you have to make sure to have additional safety precautions. We defined risk groups are exempt, low risk, moderate risk, and high risk. And you can keep in mind that usually when you're using white LEDs, you're in the exempt group. But if you're planning on using UV LEDs or high intensity blue LEDs, then you might most likely run into the topics that you need additional safety precautions. After we have looked at electrical and photobiological safeties, I wanted to talk to you about the thermal safety against hot surfaces. Again, this is a topic which is easily overlooked, but might cause trouble in your luminaire design. The reason is that it's required that all the accessible parts of a luminaire need to be below a certain temperature depending on the material. For example, if you have a lamp on your desk, then it's to be expected that this lamp will be touched by the user in order to modify the direction of the light. And thus, it's not allowed to have metallic surfaces above 60 degrees, for example, a heatsink, or plastic surfaces above 75 degrees. Whereas if you're designing downlight, then it's not to be expected that the download will be touched during normal operations. So be aware of what is the application of your luminaire, and to design the thermal isolation in accordance. Lastly, with regards to operational safety, we want to look at the safety in case of electrical failure. The 3 points before were all during normal operations, but what you also have to keep in mind is how your luminaire, how your light source will behave in the case of an electrical failure. Let's look at a common implementation of a constant current luminaire light source. You see there are a couple of LED strings and all of them are connected in parallel. Let's now imagine what happens if one of those LEDs shorts closed, so there's a short circuit in one of those LEDs. In this case, you will see that those strings get a different forward voltage because all of those strings, there are 4 LEDs, and in one of those strings, there's only 3 LEDs. And now, since all of those LED strings are connected in parallel, all the power of the whole light source will go through one of those LED strings instead of being distributed amongst all of the LED strings. And since, of course, your luminaire is not designed for the whole power to go through one of those LED strings, there might be a catastrophic failure. And this is not just a theoretical one, this is a practical safety hazard. Since overloading one of those LED strings might cause smoke, might cause heat generation, which also might cause plastic optics to start dripping down on the user. And this is, of course, a fire hazard, and you need to take additional safety precautions. One of those possible safety precautions is using a matrix connection, where you see that behind every LED in an LED string, there's a cross connection. So if there's a short failure on one of the LEDs, then the current on this LED, okay, will go through the short-circuited LED, and all the LEDs in parallel will remain darkened, but the load before will not be concentrated on the 3 LEDs on the string, but evenly distributed across the whole LED module and thus not cause a fire hazard. Now that we have talked about operational safety, I would like to give back to Paul to talk to you about different dimming technologies.
Thank you very much, Volker. Dimming is a very important aspect for all general lighting applications, especially in private homes. Deep dimming, so to dim very deeply into low areas, is very important. And I'm trying to explain to you first why and how to solve this. You can see a graph over here which shows that the human eye is experiencing a non-linear response to luminosity. That means that even a very, very small amount of light can be perceived by the eye, and changes in light in very low areas are perceived by the eye with a great difference. So even at already physical brightness difference from 1% to 2%, the brightness gain is perceived by a much bigger factor than these 1 to 2% actually. In this graph, you can see already at a very low percentage, the brightness is perceived very highly. To support this perception on the eye, we usually recommend to use an inverse logarithmic dimming curve, which can control the light in very low areas of brightness very sensitively. So if you change the brightness by a very, very small amount of light, maybe just 0.1 to 0.2%, you can already perceive the brightness to be changed a lot. But the dimming technology must enable you to dim inside these very, very low brightness ranges, below 10% usually. This is problematic because LEDs are typically binned at a higher current. For example, a mid-power LED might be binned at 65 or 150 milliamp, which is a very high brightness. When you're driving many LEDs in parallel, even very small brightness differences can result in a very high actual brightness difference of, for example, with just 0.1 volt binning range, you can have a 30% brightness difference from one LED in a string to the next one. The human eye is not able to perceive these brightness differences if the LEDs are very bright. If the LEDs are very bright, your eye is blinded by the light and you're not able to perceive a brightness difference of even maybe 20 or 30% from one LED to the next one. But if the brightness is lowered a lot and the eye is very sensitive in these very low brightness regions, then the same brightness difference of maybe 20 to 30% is immediately perceived as a very big brightness difference, and you might see very much inhomogeneity in your LED strip. How to solve this? It is possible to purchase LEDs, for example, with secondary sorting, so that the brightness and voltage differences at very low currents, for example, this specific case at 1 milliamp, are binned specifically to be in a very tight and narrow range, so that the impact of the brightness differences are not as big. Secondly, you have other options from other manufacturers, such as wafer chip bin selection. So the manufacturer of the LED is actually binning the blue chip by a specific wavelength to enable a very narrow and tight result in terms of VF and brightness. And thirdly, what is very important is to also have a smart design in terms of how many LEDs you will put in parallel, how many LEDs you will put in series to achieve minimum impact on voltage binning differences. That's all about the binning, about the dimming topic. I'll give back to Volker to go a little bit more into thermal optimization.
Yeah, thank you very much, Paul. Since this is a deep dive, we also wanted to make sure to include a topic with regards to thermal optimization of your LED modules, since this is a big design consideration. First, let's look at a bit of background. Why is thermal optimization even important for us? Like many electrical devices, LEDs generate heat, and we cannot simply let the LEDs cook without consequences. But if the LEDs are too hot, we have to keep in mind that both the lifetime of the LEDs as well as the LED's performance is impacted. So in order to make sure that your luminaire gets the lifetime your customers expect, as well as the performance your customers expect, we need to take thermal optimization into consideration. To further understand the thermal consideration and optimizations, let's first look at a thermal path. As told before, on the light source itself, the heat is generated at the LED junction and then is conducted through the solder connection to the PCB itself. From the PCB itself, it again is conducted through the PCB material to the heatsink, and the heatsink and the PCB then radiates and convects those heat aware to the surrounding medium. You might have noticed that I used a couple of words describing the different kinds of heat transport, which we'll look into details now. First is conduction, which means we heat transfer through direct contact of particles. The second one is convection, which is we heat transfer by movement of fluids like liquids or typically gases like air. And the last mode of heat transport is radiation, where radiation means it's a heat transfer via electromagnetic waves, and it does not need a medium like air. Let's first look into what we have to take into consideration with regards to convection. On luminaires, convection is usually used to transfer heat from the heatsink to the air surrounding the luminaire. And we have to keep in mind that using a heatsink is not just with, you have to keep in mind the heatsink design, but also the heatsink orientation. For example, by simply rotating a heatsink fin stack, can increase or reduce the efficacy of the heatsink significantly, since those heatsinks are normally designed with a certain mode of operation in mind. The second mode of heat transport is radiation. As told before, radiation is the heat transfer via electromagnetic wave, and since every material is radiating heat, it's our goal to have equal heat transfer of all the surfaces so that you have a maximum surface for radiation. And especially for mid-power LED modules, this radiation is the most significant mode of heat transport. So by using an intelligent design with big copper areas, which will be heated up by the thermal pads of your LED, you can make sure that most of the heat is already radiated away, thus reducing the need for a big heatsink. The last mode of heat transfer is conduction, and we will go into this a bit more in detail since you have many opportunities to optimize it. Inside a light source, conduction is used to get the heat from the LED junction into the PCB and into the heatsink. And the efficacy of the conduction heat transfer depends on the thermal conductivity of the material and also the material thickness. I've showed you a table with different thermal conductivities, where you can see that copper is much more conductive than aluminum or air. But we have to keep in mind that this conductivity takes also into account the thickness of the material. So the thermal conductivity itself is not that important, but only the thermal resistance, which is the material times the thickness. So 2 points we need to understand. First, we heat capacity, which is how much heat a material can absorb. And the second is we heat thermal resistance, like how much the temperature increases when you conduct a certain amount of power through it. And free heat capacity is not that important since it's time dependent. This is only important if you have, for example, luminaires which are designed to turn on for a very short amount, and very bright and then cool down. But for normal general lighting luminaires, you only are interested in the long-term sustainability of operations. And for spotting for heat transfers, it's very easy to use thermal imaging because this gives you a big picture of the heat transfer. Now we want to look at an example for thermal resistance. As told before, the heat is generated at the LED itself. In this example, we have half a watt of power losses inside the LED. Then we have a thermal resistance first inside the LED from the junction into the solder. Most of the times you can see in the data sheets this thermal resistance as TJ to TS. Next, we have the resistance of the solder connection itself. This means normally the LEDs are placed on the copper conductor with solder, and the solder has a thermal resistance. The next is the resistance of the PCB, then of the thermal interface material and of the heatsink itself. And if we look at all of those thermal resistances, we can calculate the expected junction temperature from the ambient temperature. In this example, we have a thermal resistance of 30 Kelvin. And when we have an ambient temperature of 25 degrees, which this will result in a junction temperature of 65 degrees Celsius, which is normally no problem at all for an LED. So it's important to make sure that you have understanding of the thermal resistance of your design before you produce it, in order to make sure that the LEDs have an expected lifetime. Next, we wanted to look into the thermal resistance of the PCB itself, since next to the heatsink, this might have quite high impact on the overall thermal resistance of your whole luminaire. The thermal resistance of a PCB depends on the conductor material and the conductor thickness. It also depends on the layout of your PCB, because if you make sure that the heat generated in the LED is first spread on a big surface of copper traces before it conducts through the PCB material itself, it's easier than if you just have one hotspot, and also on the base material properties. And since there are many different kinds of base materials, Lumitronics has performed a comparative field study to give a feeling of how different materials compare here. What we have done is we have used one layout with one fixed thermal adhesive connected to aluminum block. And what is different between all of these devices is the PCB material itself. So we have one PCB material, which is a standard FR4 one-sided, and then we have an FR4 two-sided. The difference between those two is that in the second one, we use thermal vias to connect the top to the bottom to make a better heat flow. Then we have two aluminum PCBs, which are different only in their dielectricum. The one has a 2 watts per meter Kelvin, and the second is 8 watts per meter Kelvin dielectricum. And lastly, we also wanted to show you the difference between rigid PCBs and flexible PCBs, where we have, again, a one-sided and a two-sided PI PCB to be compared. When looking at the temperatures of both the heatsink as well as the TC temperature on the PCB itself, we can see some interesting developments. Firstly is what is to be expected, that the two-sided variants of the PCBs are better than one-sided PCB variants, since we are using copper to conduct heat through the PCB itself before it goes into the heatsink, instead of making the heat travel through only the PCB material, which is usually a much worse conductor of heat than copper. Secondly, what we also see, and is to be expected from our experience, is that the aluminum PCBs perform better than the FR4 PCBs. What is maybe not to be expected is that we 8 watts per meter Kelvin dielectricum doesn't really perform a much better job when we 2 watts per meter Kelvin dielectricum, and this is because in this case we 8 watts per meter Kelvin dielectricum was simply thicker than we 2 watts per meter Kelvin one. So you have to make sure that we dielectricums used are not just measured with for thermal conductivity, but with the whole material property. And what we also wanted to show you is that we flexible PCBs with PIs are comparable in performance to FF4. They are better than FF4 in this case, and they are not that far apart from the aluminum ones. So if your project is on the verge where FF4 is maybe not possible anymore, but you're hesitant to use aluminum PCBs, look into using flexible PCBs, because while PI is a much worse heat conductor than FF4, the flexible PCBs can be used significantly thinner than the FF4 rigid PCBs. So to wrap up, the thermal optimization of LED modules, keep in mind that radiant heat transfer is very effective. Use large copper areas, especially if you're not using an aluminum PCB, but FF4 or PI. Next, it's important that you estimate the thermal resistance of the LED module before you go into the design, in order to make sure you know what to expect and whether to which kind of heatsink you need to use. Next one, it's good to use thermal imaging to verifying the heat transfer. Of course, you need to make sure that you keep in mind that thermal imaging has its pitfalls. For example, there are reflectivity issues. So make sure to verify the measurements with thermal probes. But again, thermal imaging is very effective because you get a picture of the whole module at once and can spot hidden hot spots, which you might not even think of and was not measure with heat probes. And lastly, keep in mind that flexible PCBs usually surpass rigid FF4 PCBs and might also be usable to instead of aluminum PCBs for certain applications. This was everything with regards to the thermal optimization. I would like now to give back to you, Paul, with the summary of this webinar.
Thank you very much, Volker. It has been just 35 to 40 minutes we have been talking, and I guess we could have been talking a full day about those topics to really understand all the details on the IPRO registration and eco-design labeling to go more deeply into the operational safety, dimming technologies, and thermal optimization. We only had a little bit of time today, but now we do still have some time to answer your questions, which I guess we already have a few, and which might help you to understand topics which are still open to you and which need to be discussed in more detail. We have, for once, the chat area, and we have the F&A area. Please try to use the F&A area if it's working for you. So we have all the questions summarized in one place. First question from Mr. Portman. Is are measurements taken using a thermal camera trustworthy because of material reflections?
Yeah, this is a very good question, Mr. Portman. You're right that there are pitfalls with regards to thermal imaging. Thermal imaging is a tool just like every other tool. You need to be aware of these pitfalls. You have mentioned a couple ones, like reflectivity issues, and you cannot simply trust the measurements. You have to cross-check them. but it's an efficient tool to use thermal imaging since it gives you a picture of the whole luminaire, and then you can verify the hotspots with thermal probes to get a clear picture of the final temperature. So yes, in general, thermal imaging is trustworthy if you know how to handle it, and there are pitfalls.
A lot of questions coming in right now. Let me try to. Okay, first question. Next question from Mr. Höhne. How to do thermal simulation? I guess this is a pretty wide question which we cannot answer fully within this discussion. But in general, there is software which you can use to simulate in CAD your full system. You need to know the thermal properties of all materials included. So you need to have the conductivity, heat conductivity, and also the size and reflectance of the materials. But maybe Volker, you have some details to add to how to model this.
Yes, you're right, Paul, that there are normally different methods of estimation. If you really want to simulate it, then, as you've said, Paul, you need a special software, and setting up the software is quite complicated because you need the exact design of the PCBs, you need to know the surroundings, you need to know how much radiance is absorbed versus reflected back to your luminaire. If you want to just estimate it, it's usually okay to use the properties in the datasheet of the LEDs to get the thermal resistance of the from the LED inside itself, and then use the resistance of the PCB which you have measured. But yes, this is a very deep topic, just like lighting simulations.
From our practical experience, we can tell you that only in very tricky situations we tend to do full simulations of the system with the CAD software. In most cases, it is a good option to estimate the heat conduction just by using the thermal resistances of the materials from the LED to the PCB to the heat conductor to the ambient temperature, just as Volker showed to you in the presentation. This mostly gives good enough accuracy, and if you then control your system with heat probes and control your system with a heat camera, you can verify pretty quickly if this estimation gave you the right numbers in the beginning. Okay. Next question from Dr. Atul Sontake. Is there any significant heat contribution from light conversion material, such as phosphor material, and how much it is compared to lead chip and contacts related heat? This is a very deep question into the LED itself, which is not extremely easy for us to answer because we're not actually manufacturing LEDs, but using LEDs in our systems to create light sources. In general, the contribution of the phosphor in the heat management is important, but it is an aspect which we have very little control to because we are using ready-made LEDs and not producing or developing our own LEDs. And so we are usually taking into respect the effect, the electrical power of the LED. We're trying to calculate the temperature, which is then the thermal power of the LED, and then we have the information of the heat resistance of the manufacturer, and that's what we're using for the calculation. One aspect which is also pretty important for very high power LEDs is actually how much heat the light can not create only in the phosphor, but in other parts, like in optics or nearby plastics. Because if you're using very high power LEDs in the area of several watts, and the LEDs are very efficient, then there's so much light that we saw several applications in which we had to change, for example, the design of plastics or choose different plastic materials because otherwise the optics would have melted in the application. The next question from Stefan Eiselt. If flexible printed circuit boards are a thermal alternative to FR4 printed circuit boards, what is the experience regarding stable adhesive bonding over the product's service life?
Yeah, this is Paul, would you like to answer?
Please, no, please.
Yeah, this is a very good question, and we especially wanted to get rid of this fear with regards to adhesives. Of course, all of us might have experienced in the past a bad tape of adhesive which just not stuck or was put down after a couple of years. But if you're designing to use the right thermal adhesive, which is designed for the temperatures you're expected to run and the materials you're expected to bond, then this is a very strong connection. Just like with screws, for example, if you have a vibrating environment and using screws without locking, then they will get loose too. It's the same with thermal adhesives. If you're using a thermal adhesive which is not designed for the application, then it will fail. But if you're using a thermal adhesive which is designed for the application, then it will surpass the lifetime of your luminaire. And we have to keep in mind that in automotive, many parts are glued together, and automotives are in an environment where it can get very cold and very hot. So all in all, we have good experience with using adhesives for FR4 to adhesing them to the luminaire itself. We just need to make the right preparations, for example, cleaning the surface and make sure that the adhesive is designed for the material you're trying to bond together.
Yes. Thank you very much, Volker. Next question. There's a name called Mac. I don't know if that's a right name, but anyway, I'm trying to summarize the question because it's pretty long. In general, the question is it more preferable to go for a simple system design with a small BOM to really have a very solid and simple system, or to improve in terms of thermal design by using, for example, buck or boost converters, which are really creating a better efficiency in the end. And it is not easy to answer because it depends completely on the constraints of the project. We at Lumitronics like simple and long-lasting solutions. So we usually won't suggest using a complex buck converter to run LEDs if the constraints of the project also allow a more simple project design. But if the system efficiency is making such a converter mandatory, then naturally we'll need to look into using it and find a solution. Especially due to the EPRIL and single lighting regulation constraints, we see that in the field, most of the light sources are actually extremely simple, because only with an extremely simple light source, which mostly contains just of a few LEDs on a PCB and maybe some connectors, you can achieve the highest product efficiency class. Let's discuss your product requirements, your constraints, and see what can we do as a best solution. I think this question can't be overgeneralized. Next question from Markus Zanon. Have you checked the influence of the orientation of the PCB itself on the temperature, especially in case of the design without heat sinks?
Yes, while we have not looked into this and this field study because we wanted to minimize the variables we look in which change from material to material, so we can really focus on the base material itself. The orientation of a PCB, of course, also has an effect on the cooling because depending on the orientation, the air convection is different. Nevertheless, most of the times the orientation of a PCB is given by the design of the luminaire because most of the LEDs are designed to emit light up. Some are designed to emit lights to the side, but nearly all of them are emitting light up. So you naturally also design your PCB to point in the direction where you want your light to shine. But yes, this has an influence on the temperature.
Next question is from Faisal Rahimov. How economically reasonable is it to use graphite for heat dissipation, UV LEDs? We have used graphite heat conductors in various applications. Usually we tend to use those if we have a rigid PCB, which is screwed to the heatsink, because with the graphite foils, you usually or very often don't have a glue included. If you want the best heat transfer, actually those graphite foils are usually used in very, very demanding situations. So if you have a very high heat generation and need to stay at very stable low temperatures at the chip, then this is a pretty good option. Volker, maybe you have any experience to add?
Yes, since the question was also directed into the economically of using those, they are generally more expensive than other modes of thermal interface material. So you don't choose them unless you have to. So it's economically to use them if you have to use them instead of not reaching your product design or making it much bigger. But of course, if you can get away with another kind of heat transfer, for example, paste or just an adhesive foil, you prefer to use those.
Thank you. Next question from Marko Mladenovic. Regarding the photobiological safety, the IEC 624717 test report is officially available for use. Is its use mandatory for compliance? If not, when will it become obligatory, and will application groups replace the current risk groups classification, or will both be used in parallel? I'm not sure, Volker, if you have the detailed knowledge on the exact
And not out of my head, but I'm sure we can get back to you with regards to this in the aftermath.
Yes, I think sometimes it can be tricky to know the exact numbers when which one is applicable. But Mr. Mladenovic, we will come back to you after the event to specify in clarity. The next question from Christian Höhner. If we want to go to a lifetime of 10 or 20 years, what needs to be considered? 10 to 20 years, it's a pretty tough requirement. Most importantly, I think it is to see what type of components in your luminaire, in your product, have critical aging aspects for 10 to 20 years. The LED itself can easily withstand a lifetime of 10 to 20 years, even if run at a very long extended time per day. So firstly, it's always very important lifetime of 10 to 20 years. How much is the LED actually lit up? Is it permanently lit up? Then 10 to 20 years is a very long time. But LEDs can sustain lifetimes of hundreds of thousands of hours, theoretically. More critical than the LED itself are other aging components. For example, if you have a complex electronic, then there is components like electrolytic capacitors, which typically are absolutely impossible to withstand such long lifetimes. And also glue, we have talked about adhesive solutions, is usually not suitable for a lifetime of 10 years and longer. So it is really mandatory to look into the full system design and extract the lifetime of each component. The LED itself will be able to support a lifetime of 10 or 20 years and more, but other components might be more problematic. Next question. Again from Marko Mladenovic. Does FR4 offer any thermal management advantages over Chem3?
Yeah, FR4 and Chem3 are quite comparable with regards to chemical thermal properties. FR4 offers slightly higher thermal conductivity, but mostly you use FR4 for the mechanical advantages and also the fire rigidity advantages compared to Chem3, not the thermal advantages.
Then Markus Zanon was giving a little bit more detailed questions about the orientation of the PCB. I'm not sure, Volker, if you have a short answer, or maybe we should go into a discussion more deeply.
Yeah, I
Mr.
think
Zanon.
those are very interesting questions, but I am not sure if they are generally applicable. So feel free to mail me a quick a mail after the webinar, and we can join in the detailed discussion here.
Yeah, I think it's really important to understand your product design a little more in detail to really give a solid answer to this. Let's see, we already have past 11, but we still have some questions open. Let's see. There is a question from Benjamin Südholt. When ordering LED modules, what is the limiting component of thermal management? Even if a powerful heatsink is added and internal materials may impose the limit. Additionally, how would pulsed high power operation influence material choice? I don't know. Volker, do you have a quick answer?
I wanted to focus on the last point. What to take in consideration when using high power pulse operations, then you should look also more into the heat capacity and not just of the thermal resistance, because depending on your duty cycle, it might be more economically efficient to just make sure that your components can absorb the heat and then radiate it away in your off duty cycle, then design a system which can which would be capable to cool away with 100% duty cycle.
Thank you. In general, the PCB is a very important component of the thermal management, and it is a little bit difficult to simulate or estimate because it's usually custom designed to the specific light source, and it is a complex a piece of different materials, from the copper to the glue to the CAM or PI or aluminum substrates. So when doing the design of a LED module of a light source, the PCB is usually the most tricky part of the thermal design. Next question from Tamino Scheucht. Did you test the thermal conductivity performance of thermal paste versus thermal pads for PCB to heatsink mounting? We prefer pads because the ease of use, but is there a significant difference?
Yes. While we have looked into this, results are not shared here because of brevity, but this is a very good question. Generally, paste offers you better performance in the optimal case because you can just spread paste so much thinner than pads, and it will just cover the irregularities of your surface, so giving you the best heat conductivity. However, this is the optimal case. Inside a production, the application of paste is much more tricky. Also, the correct application of paste is much more tricky than pads. So in practice, those theoretical advantages might go into practical disadvantages since you don't have the process security. So if you need better performance than available with thermal pads, then you might need to use paste, but as long as you can get away with pads, this is the easier process to use.
One thing which we can also share to you in a private discussion afterwards, which is a quite interesting thing we have learned over the time, is that in many cases, thermal pads actually have a lower heat transmission and a less good effect than just not using anything at all. So you might be worse off using a thermal pad instead of just screwing aluminum PCB to the heatsink and leaving the air gaps in between. So be aware when using thermal pads to choose those which really have a very high heat conductivity and which are very thin. So it doesn't really help you that they have a very good heat conductivity if you're using too big materials. Next question from Benjamin Südholt. Could you please explain what binning does exactly on a technical level and how to control influence it? I'm not 100% sure what of the meaning of your question. Maybe you're referring to the binning of the VF or the binning of the wafer wavelength to control the VF in very tight tolerances in low current areas. Manufacturers of the LEDs are offering a lot of different options to have a very tight and very narrow binning, for example, for the VF, but also for most of the other relevant specifications of the LED. It is very important to talk to our suppliers, to talk to the manufacturers of LED, to find out what is the options and the boundaries which they can offer. I can tell you a lot of possibilities are available which are not transparent in the data sheets which you can see on the official websites. So let's dive into detail of your requirements and we can find out what's the best option for you, which is available. Next question from Stanislav Nickel. If I sell a luminaire in which the LED PCB is defined as the light source and a dimmer is integrated, how do I specify the SVM and the PST-LM value?
Yeah, for stroboscopic measurements and also with flicker sensitivity are also regulated and how they are specified, but again, just as with the light source itself and with the separate control gear, there are many exceptions and loopholes to be aware of. So it would be best if we can have a private discussion in the aftermath to look into your specific case to make sure what is integrated, what is not integrated, how it is connected, and how it can be specified.
Yes. In many cases, the definition is actually based on the LED light source, so the PCB, the LED PCB itself, and can be pretty easy and pretty fast forward, but we'll need to look into the whole system design to be sure this will be feasible. And you also asked where do I place the energy label if I sell a luminaire but declare the LED PCB as a light source? This is pretty simple and easy to answer. If you have a luminaire with a separate light source, then you declare on your luminaire packaging this luminaire, this containing product contains a light source of energy efficiency class X, whatever it will be in detail, and the actual energy label for the light source is dedicated to the light source itself. So it is on the packaging of the light source. If you have a light source integrated into your luminaire, then it is only to be found on the internet and in the April database. I find one last question. Traditionally, what are LEDs more susceptible to? Thermal mismanagement or electrical mismanagement? That's a tough question to overgeneralize. It's not easy because we have seen problems in both areas. Actually, most cases of electrical mismanagement lead to thermal mismanagement. So the thermal requirements of LEDs to have a long lifetime of LED should not be too hot in the end. And if the LED dies, it in many cases or in most cases will die over time in very close relation to the temperature. But too high temperature is in many cases not caused because of the actual thermal mismanagement of the design of the PCB or something like this, but of mismanagement of the electrical layout. So it is difficult to answer in more clarity than this, but maybe Volker, you have something to add.
I think what you said is completely correct, and that's a good answer. What I wanted to add is that traditionally, not all the LEDs had integrated protection devices, but now for more modern LEDs, some protection like Zener diodes are already integrated in the LEDs, so those products get more and more robust.
Yes. There is a lot of electrical failure modes such as ESD, which might cause a fatal damage on the LED, but we don't see those electrical failure modes in our products because they are pretty easy to avoid actually. On the market on overall, I think they might be there actually, but I can't estimate which effect is more relevant in the total market. Okay, we already have 11:16, so we had a half an hour of discussion and questions. Thank you very much for all of your questions. I hope we had been able to reply to some of them to your help. But we are looking forward to receive more questions, to receive more discussions, and opportunities to design and produce light sources for your specific application. Just contact us by email. Or on our website, you can contact us and also book meetings directly. We're very much looking forward to receive your inquiries, and you will also have the possibility to download the presentation and to download the video of this webinar to look into the details once more. Thank you very much, and have a nice day and a nice rest of the week.
Bye.
Goodbye.